Hi, I'm Dr. Incognito. In this video, we're going to discuss the chain rule. The chain rule is used to find the derivative of a composition, f of g of x. A composition is one function inside of another. So a function followed by a function. You have g of x here inside of the function f. So if you were to take a value of x and plug it into the composition, then you would first do g of x and then get a result, and then plug that result into the function f. Here are some examples of compositions of functions. We have here the sine of 4x. So we have the 4x function inside of the sine function. If you had an x, then if you wanted to compute the sine of 4x, you would first do the function 4x, that would be the g of x, the inside, and then you would do the sine of whatever you got for 4x, that would be the outside, f. In the next example, e to the minus 2x, the negative 2x function is playing the role of g, and the exponential function is playing the role of f. If you were to take an x value like 5, the first thing you would do is negative 2 times 5, which is negative 10, so that would be the g of x, and then you would take that and plug it into the exponential function, e to the negative 10. So that would be the exponential function would be the f. So the inside is negative 2x, the exponential function is the outside. In the bottom one here, we have 1 minus x squared inside of the square root function. The 1 minus x squared is playing the role of the g, and the square root is playing the role of f. So one function is inside of another. This is a composition. And what we want to learn here is how to take the derivative of a composition. The derivative of a composition. And the formula is called the chain rule, f prime of g of x times g prime of x. So this is how we take the derivative of a composition. It's basically the derivative of the outside times the derivative of the inside. The outside function is f, and there we have its derivative f prime, and then times the inside function was g, and there we have its derivative g prime. So it's the derivative of the outside times the derivative of the inside. One thing you'll notice when we're doing the derivative of the outside, it's not f prime of x, it's f prime of g of x. So we're leaving the inside in. To start with, g of x was already inside f. So when you take the derivative of f, you leave g of x inside of f prime. So the derivative of the outside, you leave the inside in when you take the derivative of the outside. So let's see if we can do these three examples here. Suppose we want the derivative of the sine of 4x. The outside function is the sine function, and its derivative is the cosine function. So the f prime of g of x, the f is the sine function, f prime is the cosine function, and instead of writing cosine of x, I want cosine of g of x, cosine of the inside. So that's cosine of 4x. That's the f prime of g of x. I took the derivative of the outside function, the sine, I got the cosine, and I left the inside in. The 4x was inside of the sine, the 4x goes inside of its derivative. And then times g prime, times the derivative of the inside. The inside g of x would be 4x, its derivative is 4. So the cosine of 4x times 4. Or you could rewrite it 4 cosine 4x. The derivative of e to the negative 2x. E to the negative 2x. The outside function is the exponential. That would be the f. The derivative of the exponential is itself. So instead of e to the x, I'm going to leave the inside in. I'm going to have e to the g of x. So that's going to be e to the minus 2x. That's the derivative of the outside, leaving the inside in. The derivative of the exponential is itself, so that part didn't change. But then times the derivative of the inside, which is negative 2. So negative 2 e to the negative 2x. For the derivative of the square root of 1 minus x squared, the outside function is the square root, and the derivative of the square root of x, you can use the power rule and get 1 over 2 root x. So I'm going to write my derivative like that rather than using the 1/2 power and the negative 1/2 power. So the outside function is the square root. The derivative of the square root function is here. So I want the derivative of the square root leaving the inside in. So instead of square root of x here in my derivative, I'm going to have square root of g of x, which is the inside function here, 1 minus x squared. So 1 over 2 root 1 minus x squared. That's my f prime of g of x, the derivative of the outside leaving the inside in. It's not 1 over 2 root x, it's 1 over 2 root g of x. F prime of g of x. And then times g prime of x, the derivative of the inside function. The inside function is 1 minus x squared. The derivative of that is negative 2x. And this time we have a simplification. 2 over 2 cancels. So we have negative x over the square root of 1 minus x squared. Let's look at a couple of other examples. How about the derivative of, let's say we have a cubic polynomial. Let's say we have this cubic polynomial raised to the 8th power. And we want the derivative of that. So this function is a composition. The cubic polynomial is sitting inside of the 8th power function. So the outside function is the 8th power function. That would be the function f. And the inside function is the cubic polynomial. That would be the function g. So we begin with f prime of g of x. So f again was the 8th power, and to take the derivative of the 8th power, you bring the 8 down and make it a 7 using the power rule. So I'm going to have 8 and power 7. That's how you take the derivative of the 8th power function. And then instead of just putting x in here, 8x to the 7th, I want f prime of g of x. So I want to put g of x inside of the derivative here. So I'm going to copy g of x, x cubed plus 4x squared minus 3x plus 7. And then times g prime of x. So the derivative of the cubic polynomial that's inside of the 8th power. So the derivative of this cubic polynomial is 3x squared plus 8x minus 3. So there is our derivative. The derivative of the outside, leaving the inside in, times the derivative of the inside. Another example, the derivative of tangent squared x. Tangent squared x. So for this one, we have to recognize the inside and the outside correctly. The tangent function is inside of the squaring function. Tangent of x squared could be written as tangent of x quantity squared. So we don't usually write it like this because this is a convenient place to put the exponent, but we could put tangent of x in a grouping symbol and then put the square there. That would be the tangent of x squared. And in this format, it's a little bit clunky, but it's clear that the tangent function is inside of the squaring function. Tangent squared x, if we had an angle like 45 degrees, first we would do the tangent of 45 degrees, and then we would square it. And the one you would do first is the inside function. With f of g of x, if somebody gives you an x, the first thing you do is the inside. So if somebody gave you 45 degrees, you would do tangent of 45 degrees, and then you would square. So the inside function is the tangent function, and the outside function is the squaring function. You could write it like that. You can see it that way. Although we don't usually write this because it's clunky. So the derivative of the outside is 2 tan x to the first. The derivative of x squared would be 2x, but here we want to leave the inside in. Instead of 2x, I have 2g of x, 2 times tan x. So that was my f prime of g of x. And now times the derivative of the inside, so we have to remember the derivative of the tangent function is secant squared x. Secant squared x. And this secant squared, that means the secant of x quantity squared. But there's our answer. The derivative of the outside times the derivative of the inside. Let's contrast that with the tangent of x squared. It's the same two functions being composed, the tangent function and the square function, but we're switching the inside and the outside. Here the inside function is x squared, and it's a little bit more visually obvious because the x squared is already in parentheses. And the tangent function is the outside function. Of course, what I want to do with this is I want to take the derivative. So the derivative of the tangent of x squared. The outside function is the tangent, its derivative is the secant squared, and leave the inside in. So secant squared of x squared. And then times the derivative of the inside is 2x. And let's try one more example. Let's take the derivative of e to the minus x squared. The derivative of e to the minus x squared. In this situation, minus x squared is inside of the exponential function. If somebody were to give you an x like 4, the first thing you would do is put the 4 in here and get 16 minus 16, and then you would do e to the minus 16. So the inside function is negative x squared, that's what you would do first, and the outside function is the exponential, that's what you would do second. So the derivative of the exponential is itself, and leave the inside in, it just leaves this whole thing alone, e to the minus x squared. And that's because, again, the derivative of the exponential, e to the x, is e to the x. But instead of e to the x here, I want e to the g of x. E to the inside, so that stays exactly the same in the first step. That was f prime of g of x. Now I want g prime of x. So g prime of x is the derivative of negative x squared is negative 2x. So our derivative is e to the negative x squared times negative 2x. Okay, so there's a first look at the chain rule. Thank you for watching.